we need to adapt our thinking from continuous Fourier transform to discrete Fourier transform. Yeah. And our understanding, we also need to use the discrete thinking, yeah, for our real-world applications. Most of the time, we need to do discrete data processing because the data format given currently in digital era, right? So most of the data people collected, digital data. Yeah. So when we consider that, so our mathematical tools, we also need to adapt our mathematical tools friendly to the form of the data. All right. Here, last time, when we use the, so what's that function? Complex trigonometric polynomials, right? So last time, yeah, we talk about the complex trigonometric polynomials. This, E function here, yeah. Sum of several terms of an E function. Yeah. So last time we used the data modeling understanding. Yeah. So we imagine, so this is our data modeling function. So that's one way to look at the problem, data modeling. Yeah. All right, but there is another way. Yeah. So usually we use multiple views to understand important concepts. All right, another view, this view, okay, yeah. Discrete Fourier transform. So this view, in this transform view, yeah, so now we do not use the data modeling view, okay? So we change to transform view. It's a different view. Yeah. So in this transform view, let's look at the data. How do we transform our original data? Yeah. So our original data, sequence, finite sequence. It's not an infinite sequence, right? So here we consider our data is a finite sequence. Yeah. So the finite sequence, these capital N data points. Yeah. So that corresponds to capital N data points. Yeah. So we put the function values of the N data points in a vector. Yeah. Column vector, transpose. Yeah. Because for when we write a vector, if we use the row vector to write it, we can save a lot of space. Yeah. So that's the main reason. But our default vector is a column vector, right? Yeah. So here we use the transpose. Yeah. So it's a column vector. All right. So then we apply discrete Fourier transform on the given data in the form of a finite sequence. And the result, yeah, the data form changed in a different domain. Yeah. So now we go to a different domain. In different domain, we get another vector of data or another finite sequence and dimension with the same dimension. Yeah. So here. So that's the first thing in our understanding. So when we do data transformation, we do not change the dimension. Okay? Yeah. So here you can understand. Basically, so here we call the no loss change, lossless. Yeah. So sometimes people call lossless, no loss, no data loss. Okay? Yeah. Lossless, this concept people use in data processing. Yeah. here. Yeah. Lossless. Yeah. This is a lossless transformation. Yeah. All right. Yeah. Because we need to recover. We need to go back. Okay? After the data processing, we need to get back to the original domain to interpret our data. Yeah. All right. So for this kind of lossless transformation, if we do not change, yeah, sometimes you need to change, sometimes you do not change. Yeah. Yeah. Actually, most of the time you need to manipulate your data in the different domain, frequency domain. Yeah. So you need to change it. Yeah. If you do not do any change, think about what's the point. You cannot get anything new, right? You cannot improve anything if you do not change. You only read, you only study. Yeah, that's possible. Yeah, so you do not change it. You only read information. Yeah, so that's possible. Yeah, some applications, you do not need to make change. You just extract features. Yeah. That's also useful. Extracting features from the given information, also useful. Yeah. But most of the applications, we need to change the data. Yeah. We need to, slightly change the data. Yeah. All right. So then, at the end, you need to apply the inverse discrete Fourier transform to present your data in the original time domain or spatial domain. Yeah, not frequency domain. Yeah. The final interpretation occurs at the time domain or spatial domain. Yeah, not a frequency domain. Yeah. All right. So that's the typical process. All right. Yeah. So the one general understanding. Another one here. Understanding. Look at the form when we do transformation. Yeah. So each Cn coefficient, yeah, Fn hat Cn, the relationship just a capital N multiple. Yeah. So you can treat them, this kind of very close relationship. Yeah, essentially, just scale up by N multiples. Yeah. All right. So you can see each coefficient in the frequency domain is represented as a summation of certain terms. Yeah. So this one, when we compare it with the continuous version of Fourier transform, yeah. So we use integral. Okay, yeah. Although negative infinity to infinity, yeah. F, yeah, here I use F hat, okay. W negative I W X dx, right? Yeah. So that's our continuous version of the Fourier transform. Now let's compare the discrete version of Fourier transform. Summation, integral, yeah. All right, yeah, yeah. And yeah, so typically, when we convert our data from continuous form to discrete form, yeah, so the integral operation and the summation operation, yeah, you know, they are corresponding each other. Yeah, yeah. All right. Yeah. Yeah, but here, this f hat function, Fourier transform, this is already the whole function, right? Yeah. So in the frequency domain, that's the whole function. But here it is just the one coefficient, right? Yeah. One of the capital N coefficient. Yeah. But we need capital N such coefficient. Yeah. A vector of that. Yeah. Not just one. Yeah. But this one, although here, yeah, so we want to get a good understanding. Although it is just one, but this one, you can see this one, the reason this individual coefficient, comes from a special xk, right? Yeah. A special xk. Yeah. So here, yeah. But because when you change, special n, sorry, subscript n, then you use n here. So for different subscripts, you replace those subscripts in that exponent part. Yeah. So here you can see, although all these coefficients, we need to calculate capital N such coefficients, but just for different subscripts, right? So the framework is the same. Yeah. The general formula is the same. Yeah, but we just plug in different data locations. Here we call data locations, right? Yeah. For different n, little n multiple of xk. Yeah. So because xk here. Yeah. So what's the xk? Xk, right? Yeah. Xk. That's the xk. This xk we call the sample locations, right? Yeah. So the given data, so we call the sample locations. All right? Yeah. Sample locations. All right. So there, when you calculate different discrete Fourier coefficients, you just use different sample locations, right? Yeah. So here you can see different sample locations. But little f sub k, the original data vector, you do not change the coefficient part. The coefficient part you do not change. Yeah. So you only change the E term part. E term part. And when you change, there is a nice rule there. So when you change, it's not a random change, right? It's not a random change. Okay? Yeah. So the integer multiple. Yeah. So the subscript number is used as integer multiple on your sample locations. Things like that. Sample locations, right? Yeah. Yeah. So in that way, you can see, yeah, so although we need to calculate capital N times, but basically, these capital N times, we just try to pick up all the information from the original data. Original data, there are N items, capital N items. So then, in our new domain, we need to preserve the same amount of information, right? Same amount of information. So it should be still capital N data items. Yeah, yeah. So that's fair, right? Yeah. No gain, no loss. That's fair. Okay? Yeah. Yeah. So that's the right way. Yeah. All right. So only when there is no gain, no loss in your transformed domain, then you can recover. You can do the complete recovery if you want. Yeah. So all right. Yeah. Then, next, inverse transform. Yeah. All right. So this time you can see the matrix representation helps a lot. Yeah. Otherwise, if you need to write equation, this summation type equations, for all these n numbers, it's not concise way, right? Yeah. So it's not a good way. Yeah. So in math, under this situation, we like to use abstraction. We like to represent our data conceptually. So using very concise representation. Here, this is our concise representation. Yeah. Matrix multiplication. Yeah. Input a vector, output also a vector. Okay? Yeah. So this is your input vector. Little f, boldface f, input vector. This is output vector. All right. How to connect input vector and output vector? Yeah. So you have a system. Yeah. Your transformation. Yeah. So that's the, a special system. Yeah. So your capital F sub n is a square matrix. Yeah. Capital N by capital N, square matrix. All right. And this matrix must be an invertible matrix. Invertible matrix. Because you need to consider the inverse transform, right? Yeah. Inverse transform corresponds to the inverse of your coefficient matrix. This is capital N. Okay? All right. Yeah, so you can also treat this coefficient matrix as a, transition matrix. Yeah. From one domain to another domain. Yeah, all right. So invertible. Yeah. Then, so here, let's review linear algebra a little bit. Linear algebra knowledge. Yeah. We know in linear algebra, when we use matrix, coefficient matrix, to multiply a vector, we call it linear transformation, right? Yeah. That matrix operation, so we have another understanding using the transformation view to understand. So that is our linear transformation in linear algebra. Yeah. So a linear transformation, there are definitions. So what is the definition of linear transformation? Okay, so preserve linearity. Yeah, yeah. So all those basic rules we need to follow. Yeah, but following all the basic basic rules of linear transformation, yeah, we can show one linear transformation corresponds to one matrix. Yeah, so that's a one-to-one correspondence. Any linear transformation can be represented by a matrix. Yeah. A matrix is not necessarily a square matrix. It could be a rectangular matrix. Okay? Yeah, it could be a rectangle. So the general situation, it could be a rectangular matrix. All right. For example, yeah, if I use y vector equals capital A times x vector. Okay? If n vector, if it is n-dimensional, okay, n-dimensional, y could be different dimensional, right? So m-dimensional. All right. Then this A matrix, you can see this linear transformation from two different dimensional spaces. Yeah. So one linear space to another completely different linear space. Yeah. So it is a rectangular matrix. This matrix is rectangular. rectangular matrix. All right? Yeah? Yeah. So it is M by N matrix. Okay? N rows and M rows. Yeah? The number of rows the same as the dimension of the y vector. M rows. N columns, the number of columns the same as the number of dimension of x vector. Yeah. So that's the linear algebra. Yeah. All right. So here, the good thing is we have a square matrix. Okay? Square matrix from capital N dimensional linear space to another capital N dimensional linear space. All right. Yeah. Yeah. So I just mentioned that our capital F matrix must be invertible. Now, think about if capital F is not invertible, what would happen? Yeah. What would happen? Not invertible. Then you do not have inverse matrix. Yeah. So you do not have inverse matrix. So then so here you can think about if our coefficient matrix is not invertible, that means its determinant equals 0. Then you do this kind of linear transformation. What will you get? What's the consequence? Here, I want to ask you, what's the potential consequence? Yeah, in the real world situation. Yeah. So here, I want to help you understand, a lot of aspects related to applications. The consequence will be, think about. Yeah. So the consequence you can see. Now, when you go from time domain to frequency domain, right? So that's the one way. Yeah. Yeah. So this is the one way, okay? Yeah. Time domain to frequency domain. Then you cannot get back. It's a one-way street. You cannot get back. You cannot recover your original data because inverse matrix does not exist. What does that mean? You cannot recover your original data. What does that mean? That means, yeah, based on logic. Yeah, now we use logic to understand. That means your transformation is not lossless, right? Your transformation is not lossless. So we can call it lossy, right? Not lossless. Yeah? Because you will lose part of the data. You will lose part of the data. Not lossless. Okay? This transformation is not lossless. Okay? Yeah? Yeah? So you know how important. Yeah. So the invertibility of the coefficient matrix, how important it is. Okay? Yeah. So we want to understand this whole thing better. Yeah. All right. Yeah. Second, all right. So now we know its inverse. We want its inverse exists. The next question, how to calculate the inverse? Another technical question we need to answer. We want to calculate the inverse. All right. And usually in the general situation, think about this capital N could be large, right? This capital N could be relatively large. So here I want to talk about how to calculate the matrix inverse, this question. How to calculate the matrix inverse. Right. Yeah. We did a two-dimensional calculation. Yeah. So in several of our examples, we calculate the inverse of the matrix for 2D matrix. Yeah. That's very simple. Yeah. So we have a formula. Yeah. Yeah. So we apply the formula, we can find the inverse of a 2 by 2 matrix immediately. All right. How about n by n? So now, our current situation, we need to calculate inverse, matrix inverse for n by n matrix. Okay? Yeah. Also, there is a formula. Okay? Yeah. The formula exists, n by n matrix. Yeah. So in linear algebra, you can find the formula. Okay? Yeah. Yeah. The formula, you need to calculate determinant first. Okay? After you get determinant, then you need to write the matrix, result matrix. Each entry, you need to calculate another determinant. Yeah. But although the formula is very complicated, but there is a formula. Yeah. And we can apply computer programs, computer software to calculate. Yeah. So we do not need to use hand calculating. Yeah. So nobody can do the hand calculating easily. Yeah. A lot of tedious work. So nobody wants to do it. Yeah. Yeah. All right. So there is a question. Yeah. Even if we can apply software, programs to do the calculation, still there is a question: how fast you can calculate it. Okay? Yeah. Especially when the size of the matrix is very large, how fast you can find the inverse of a matrix by applying the formula. Okay? Whatever method you use, matrix inverse. Okay? Yeah. Here, I give you a result. Yeah. Because I want to extend your knowledge a little bit, related. Yeah. So that in the real world applications, so you can, so at least you have some background information. Yeah. All right. Now, because they are not computer science students, so when people talk about efficiency of the calculation, how fast certain algorithm can run, so people use asymptotic notations. Yeah. So here, I just explain in a simple way. All right. Asymptotic notation, one is people use big theta. Big theta of capital M, its meaning, yeah, you just understand meaning. It's a certain constant C times capital N. Okay? That's C1, 2, so it's not important. Just a certain constant C times that capital N number. Okay? So that's the, you can see how fast is the algorithm. But the matrix inverse, if we use asymptotic notation to see how fast your calculation. Big theta of capital N cube. How slow it is. N cube. Okay? Yeah. So think about if capital N equals 1,000, N cube 1 billion, right? Yeah, yeah. That many multiplications, all right? So let's think about. Suppose you need to calculate matrix inverse, 1000 by 1000 matrix. You want to invert it, okay? Apply computer program, or, yeah. So the program, powerful computer, but you need to do this many, 1 billion, this many, multiple of 1 billion, yeah? Because there is a C, right? C means multiple. Multiple of 1 billion of multiplication. You need to do that large number of multiplication. How slow it is. Think about that. Okay? Yeah. But that is for the general matrix inverse. Okay? So here I'm talking about the general matrix inverse. That's slow. That's slow for general matrix inverse, not for special. For special matrix inverse, yeah, so here, special means when our matrix has some special structure, we can take advantage of the special structure. This matrix, fortunately, this capital F matrix, there is a special structure. So special. Okay? Yeah. Each entry, power of little w, we know little w is that. Okay? The structure is so nice. Yeah. Then, its inverse, you do not need to do calculation. Right? You just do some simple math operation. Next slide, we will see its inverse. You only need to do a simple math operation on that matrix, you get its inverse. Because it's a special matrix. It's not a general matrix. Okay? Yeah? Then, extremely fast. Very fast. You only need to change the sign, flip the sign. Or matrix transform, easy, right? Yeah. Transform, you just copy entries to different locations. Then change a sign, it's easy, right? Then you get its inverse. Because the structure is so simple, so special structure. Okay, yeah. So here, another thing is we like this matrix because we can easily write out its inverse. We do not need to, use our formula, right? So because there is an inverse formula, so don't apply that formula. Too slow. Too slow. Okay. Yeah. All right. Yeah. All right. Next. Now, understand inverse on Fourier matrix. Yeah, this time, we want to get more information about the matrix inverse. Yeah. All right. But we need to have some basic knowledge of complex numbers. Yeah. So here I just review a little bit. Yeah. Basic knowledge of complex conjugate. Oh, so the general complex number, most of the time people use z. Yeah. So this z variable, yeah. So people like to use to represent a complex number. Complex number, the typical structure of a complex number, two parts, real part and the imaginary part. Little a, the real part. Yeah, little a is a real number, real part. Plus b, another real number times little I, so a root of -1. Yeah. So this is the general complex number. All right. Then it's conjugate. Yeah. Conjugate, most of the time we use this bar, okay, on top. Yeah. Z bar. Yeah, put a bar on it. Yeah, so that's the typical notation from the conjugate. Conjugate, we just change the sign of the imaginary part, from plus to minus. Yeah, that's the complex conjugate. Yeah, all right. Yeah, then with this operation, yeah, now we can. This time we apply the complex conjugate on our little w, yeah, little w. So our only little w, our original little w, there is a negative sign, right? Yeah. So our original little w equals e to the negative 2 pi I over capital M. Yeah. When you take complex conjugate, you just change the sign of the exponent number from negative to positive. Negative to positive. Yeah? Yeah? Yeah, it's easy to see. Yeah, if you use Euler's formula, it's easy to see it. Okay? Yeah. Yeah, so let me review a little bit. For some of you, so Euler formula, e to the I theta, right, angle, equals cosine of theta plus I times sine of theta. Now let's calculate e to the negative I theta. Cosine of negative theta still cosine theta, right? But the sine negative theta becomes negative sine theta. Okay? You can see they are conjugate each other, right? Yeah? So you can see when we change the angle at the exponent, we only change the sign of the angle at the exponent. Then we get a conjugate. Yeah. So here, yeah, the conjugate here. Okay, all right. The reason here we use the conjugate concept because the inverse of that capital M need to use this conjugate. Inverse capital F matrix, we need to use conjugate. Yeah. All right. Yeah. Now, yeah, yeah. So let's do step by step. So we do not jump to the inverse immediately. Yeah. So let's just move toward the inverse step by step. The first step, we calculate the conjugate of that capital F matrix. Yeah. F bar, yeah, each entry we take conjugate. Okay? Each entry we take conjugate operation. Yeah. All right. So that's this one. Then, next step we need to do transpose. Yeah. So after we take conjugate, yeah, yeah. All right. So here, all right. Yeah. So yeah, actually here we do not take transpose here. Here you can see there is a key property. The conjugate, you do multiplication in this way, you get a capital N times of identity matrix. Then you almost get the inverse, right? Yeah, you almost get the inverse. Yeah, yeah. All right. So this key property we can do verification easily. Yeah. So you just calculate multiplication. Yeah. By the definition of matrix multiplication. So row, column, do multiplication. Then, but you need some math techniques to get the answer. Yeah. All right. So then this formula, we can get an inverse matrix immediately. Inverse just 1 over capital N times capital F conjugate. Think about how fast. Yeah. When we calculate this inverse, how fast it is. Yeah. Conjugate fast, right? Yeah. Conjugate because you just change the sign. Okay? From plus sign to minus sign. Yeah. Yeah. Here, and we do not need to do transpose. Yeah. So after we only change sign, then but we need to multiply 1 over capital M. This operation, very fast. Yeah. So we don't worry about, computation part. Yeah. All right. Yeah, so here, as a simple example, so 4 by 4, yeah. 4 by 4, yeah, based on the definition, so you can see, yeah. 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 So the entry, yeah, so do multiplication, and this kind of matrix model you can use Wolfram alpha, yeah, to calculate very fast. Yeah. Now, even on scratch paper, it's not too bad. Okay? On scratch paper, you get these numbers so simple, not too bad. Yeah. All right. Yeah. All right. Yeah. So then, yeah, it's okay. Yeah, 10 minutes. Yeah. So remaining. So now we need to B.3 solve ODEs by Fourier series. So we need to look at some application questions. This discrete topic, next class, yeah, actually not next, another class, yeah, next week. Next week we have 2 classes, so I will do 2 topics. Yeah. But another topic, I will continue the discrete Fourier transform. There is another important topic called fast Fourier transform. Fast. What is the fastest way? Because the fast Fourier transform, people call it FFT. Yeah, so it's a very big, important technology in engineering. Yeah, so next week, second class, I need to talk about FFT, fast Fourier transform. Some special algorithm that can speed up calculating the discrete Fourier transform in the fastest possible way. Yeah. Yeah, but later I heard, some MIT people develop another faster, faster than FFT. Yeah. Yeah. But so far in engineering, when people do discrete Fourier transform, people apply FFT. Yeah. So all of software contains FFT. Yeah. So we need to know the basic theory behind FFT. Yeah. Yeah. So, yeah. All right. So that's next week. B.3. Now we solve ODEs by Fourier series. Yeah. All right. Yeah. So here, so the idea. So here. Idea is pretty simple. Yeah. Now we have all our knowledge preparation ready. Yeah. So we can do more. Yeah. We have more. So this Fourier series, another powerful tool we can use in solving ODEs. Yeah. All right. So in this equation, yeah, so very simple ODE. But the R function, yeah, here, this R function is a special function. Yeah. There is absolute value there. Okay, yeah. Absolute value, yeah, so we can treat it as a piecewise continuous function. Yeah. But here, when we use Fourier series, we don't worry about this function. Yeah. So 2 pi periodic, 2 pi periodic function, okay, yeah, and yeah. So then, for the solution, now we need to use a basic property. Yeah, we need to use a basic property. Yeah, take advantage of the basic property. So what's that property? First, we calculate the Fourier series of this little r function. Yeah. Yeah, that's very easy. Yeah. We just apply the formula. Yeah. It's an even function, then we apply the even function formula. Right? Yeah. So we only have the cosine terms. We don't have sine terms. Then we calculate A0 and all the other A coefficients, yeah, by integrals. Yeah. We just calculate integral one by one. Yeah. A0, yeah, yeah, integral, yeah, because, you know, if you, for this kind of calculation, if you don't want to use hand calculating, you can use Wolfram alpha. Okay? All right. Yeah. All right. So then, AN formula, yeah, you know, yeah, yeah. You know, at the end, yeah, because you need to consider the cases, you know, even odd and even odd cases. Yeah. All right. So then your representation is slightly different for even and odd n. Yeah. Yeah. So for the odd case, A coefficients are 0, and for even case, yeah, so you have, you know, some special coefficients. Yeah. So you can represent your R function as a Fourier series, this kind of Fourier series, right? The first step. Yeah. Then the second step, so we need to use the linearity property of this ODE. This ODE has the linearity property. Yeah. So although the linearity property here, yeah, so we need to adapt our understanding different, because when we learn second order ODE, when we talk about linearity property, we emphasize homogeneous, right? Yeah, here, no. Here we need to change our understanding a little bit. Yeah, here it's not homogeneous, okay? Yeah, but here we apply the linearity property in a different way, term by term. Can we remember when we learn choice rules? We learn choice rules, right? There is a sum rule, right? Yeah, sum rule. So the R function, there are multiple terms. Then we can consider, you know, the particular solution for each term. Yeah, there is a particular solution. Sum rule, we add them together, right? Sum rule. So here, basically, we apply the sum rule, all right? Yeah, that is, let's calculate the particular solution for each term. Each term, that's easy to calculate, right? Each term. Yeah. Then we apply sum rule. Okay. So we get a complete solution. So that idea. Yeah. All right. Yeah. So let's use that idea. Yeah. So we expect our final solution should have the structure like this. Summation, sum rules, right? Sum of the, you know, part of the solutions. Yeah. Part of the solution. Okay. Each y subscript corresponds to, you know, you use just one of the terms in your R function to find that particular solution. Okay? Yeah. All right. Yeah. Yeah. So with this understanding, so we want to do a general calculation. Okay? We consider this generate yn, y sub n. Yeah. So because we know this form, right? The form is quite clear. Yeah. All right. Then, yeah. So let's write it y2k. Yeah, because, you know, for odd, yeah. So no. So, yeah. y0, yeah. y0 very easy. Yeah. Yeah. So we can find the y0 easily. Yeah. And the general term, yeah, we need to determine capital A, capital B. Yeah. Yeah. So then we do the calculation. Yeah. All right. So then capital B equals 0, capital A, so we can find some expression. Yeah. So then we can write our final solution. putting them together. Yeah. Okay. Yeah. So although, you know, a little tedious, but not too bad. Yeah. Little tedious, but not too bad. Yeah. So now you can see this is your particular solution, right? YP. Yeah. Okay. YP. Yeah. Because for other general solutions, we don't worry, right? Yeah. For questions, for ODE like this, we only need to find one particular solution. Now we're almost there. Yeah. Because the remaining, the general solution, very straightforward. Yeah. Yeah. All right. So try to, yeah. So that's the, simple way so we can solve ODE. Yeah. All right. So let's take a break. Yeah. I just have another small example. So then we finish